Most of the integrals we've done so far this year take on this form right here. In fact, I think probably, well, all the definite integrals do anyway. But one thing that we've done so far is a and b have always been numbers. They've always been finite numbers. So today, with improper integrals, there's two kinds of improper integrals. For now, we're just going to look at the type where one of the boundaries has infinity, and it could be positive or negative infinity. So let's consider 1 over x squared. So let's say we want to do the integral of 1 over x squared. I'm going to pull it up so we can look at the graph. Sorry, that's not it. Give me 1 second. 1 over x squared. Let me look at the graph. Okay, give me a second to put the zoom back on normal. Okay, so you can see kind of what it looks like. I'll sketch it right here. If you need a better indication, it does something like this. Okay, well, let's say we wanted to start, say, right here at x equals 1, and we wanted to go over to some undisclosed spot, and we'll just call it b. So we want to find the area on this curve from 1 to b. So let's solve this. First of all, we can bring x squared up as x to the negative 2. Add 1 to the exponent, divide by that number, so we get negative x to the negative 1 from 1 to b. I'm going to go ahead and move that x back to the bottom. And we plug in the top equation minus, the top number, the b, minus the bottom number, 1. So what we really end up with is negative 1 over b plus 1. Now the cool part about this is by doing it in general, I found a way to find the area from 1 to any number, and I don't have to do the integral over and over. So if I wanted to find the integral from 1 to 2, I would just plug in 2 for b, and that would tell me my area. Or if I wanted to find out the integral from 1 to 4, I would just plug in 4 for b, and that would be my area. So what if I wanted to find the area from 1 all the way to infinity? Well, we can't plug infinity into b, but we can take the limit as b approaches infinity. So that's how we're going to get around this problem. We can't plug infinity in, but we can take the limit as b approaches infinity. So if you do that, the limit as b approaches infinity, the b on the bottom, it gets huge, which means this piece right here will go to 0. 1 just stays 1. So the area from 1 to infinity would be 1. Now I know that sounds really crazy, that an area over an infinite length could be finite. The best way I can explain it to you is this. If you imagine standing 10 feet from a door, and then you walk halfway to that door, you're 5 feet from the door. Then you walk halfway to the door, you're 2.5 feet from the door. You walk halfway to the door, and you're 1.25 feet. And if you keep walking halfway each time, now in practicality or in the real world, you're going to get ridiculously close. But theoretically, if you could shrink down every time so you could actually do half the distance and do it well, you would never reach the doorway. You could take an infinite number of steps, and you would get ridiculously close to that doorway, but you would never actually reach it or pass it. The idea is the same here. Our area is going to keep growing, but in such a small way and so slowly that it's just going to get closer and closer to 1 without ever actually reaching 1. But as we approach infinity, we get closer and closer to 1. So let's do an example all the way through now that we know what we're about. So the way we approach this if we have infinity, and again, what makes this an improper integral is the fact that we have an infinity in the boundary. We replace that infinity, that improper part, with a b. I'm just choosing b because we usually call this, from a to b. So typically we replace the top one with a b and the bottom one with a, but it really doesn't matter. You can use b all the time, you can use c all the time, a all the time. It's not a big deal. Just replace it with a variable, and then out front we'll write the limit as b approaches infinity. So that's your first step. Replace the improper part with a variable and do the limit as your variable approaches what you had there. Now we go ahead and take the integral. Integral of 1 over x is the natural log of absolute value of x. And then I plug in the top minus plug in the bottom. Okay, well I don't know if you remember, but natural log of 1 is actually just 0, so we just end up with the limit as b approaches infinity of the natural log of b. Now as b is going to infinity, natural log is also going to infinity. So our limit this time would actually be infinity. So there's two terms we need to talk about right now. And those are the words converge and diverge. Okay. Converge is what our first example did. The area is a finite number. So our first improper integral, the 1 over x squared, converged because it actually had a finite answer. The one we just did diverged because the area is infinite. So we're going to be using these words a lot in Calc BC. So the idea here is converge gives you an actual number, whereas diverge gives you infinity, or sometimes in some scenarios we'll see it just gives you does not exist. I don't think that so much applies in improper integrals, but it will for some things we do later on. So converge, you get a finite number. Diverge, you get infinity, or does not exist. Okay, next example. We again have a problem because there's an infinity in the boundaries. That's what makes this improper. So I do the limit as b approaches infinity. That's the way we get around this problem. And we do e to the negative x dx. Okay, the antiderivative of e to the negative x is negative e to the negative x. Plug in the b minus plug in the 0. So this really just ends up being a plus. So that's negative e to the negative b plus 1. And we're taking the limit as b approaches infinity. Now, it's a good idea if you can do these without a calculator as much as possible. If you plug infinity into the e right now, you get e to the negative infinity. And if you think about what e to the x does, as you go this way out to negative infinity, it just approaches 0. So this piece is approaching 0, and this piece is obviously just 1, so our answer is 1. But I also want to make sure you do know how to do it in the calculator. So let me pull that up and show you. You can do it just like the limits we did in our calculator way back in Calculus AB. We can plug y equals negative e to the negative x plus 1. Sorry, I put my parentheses in the wrong place. Let's fix that. Here we go. And we go to our table, and we're trying to approach infinity. So we would want to plug in things like 10, 100, 1,000. And you can see very clearly that that is going towards 1. So just as we found, we got 1. So I would say, please try these in your calculator if you need to. But if possible, do it without. Okay, we have another one where something improper is the infinity. So we need to take it out, and we do the limit as b approaches infinity. The integral from 1 to b of 1 minus x e to the negative x. Well, if you notice, this one is a little more complicated of an integral than we've done so far, at least just in this section, because it's going to require integration by parts. So you have to use all your integral rules here. You may have to use u sub, integration by parts, you may have to use partial fractions, you may have to use inverse trig. Any of the integral things we've learned can apply here. Because if we remember LIATE, that tells us what to choose for u. A, algebraic, comes first. So that means 1 minus x is going to be our u, and e to the negative x is going to be our dv. So the derivative of u is negative 1. The antiderivative of e to the negative x is negative e to the negative x. So we're going to end up with the limit as b approaches infinity of u times v. Got a negative there, sorry. Minus the integral of v times du. So that's going to be a positive e to the negative x, because we have these two negatives here. They're going to cancel each other out. Okay, you can take the integral of that fairly easily. We get the limit as b approaches negative infinity of 1 minus x times negative e to the negative x. It'll be plus e to the negative x plus c, because we just have to divide by negative 1, so it changes the sign back to positive. So this would be a good example of one that's going to be pretty difficult to do without a calculator. So, with that in mind, we will pull the calculator up. And our equation was 1 minus x times parentheses negative e to the negative x. And then let's see, it was plus e to the negative x. So now we can go to our table, see what happens as we go toward infinity, and we actually get 0. I forgot one important thing. My mistake. We have boundaries here. We're going from 1 to b. So we don't have a plus c. Very sorry, I forgot something very important here. We've got to plug these in first. I forgot one step. So don't forget, it's easy with integration by parts to do that, because you're not used to having to have an integral on one side. We haven't done any definite integrals with integration by parts. So let's try this one more time. I apologize for that mistake. We do the limit as b approaches infinity, and then we have to plug in the b minus, okay, if we plug in 1 minus 1 is 0, so that first term just gets wiped out, and then we have e to the negative 1. Okay, now we're good. So we just have to change our equation a little bit, because if you notice, this was identical to what we had here. We just have to add the minus e to the negative 1. If you get an area of 0, that's a red flag. So that's one good thing you can think about. If you get 0, that probably doesn't make sense when you're looking over a period of infinity. So minus e to the negative 1. Okay, now if we go, we get negative 0.3679. And that actually is just negative 1 over e, or negative e to the negative 1, in case you're curious. So our answer is negative 0.3679. So this would be an example of one that converges. Anytime you get a finite number, it converges. If you get infinity, it diverges. Alright, last example. We've got two things that are improper here. The infinity on top and the negative infinity on the bottom. If you have two improper things like this, then you have to do two different integrals. So I have to split this up. I'm going to make it integral from 0 to infinity of 1 over x squared plus 1 plus the integral from negative infinity to 0 of 1 over x squared plus 1. So I have two improper things to deal with. So I'm going to have to do the limit as b approaches infinity of the integral from 0 to b plus the limit as a approaches negative infinity, the limit from a to 0. Again, if you want to use the same letter all the time, you can. I just typically use, and this is common in books as well, that you use b if you replace the top one and a if you replace the bottom one. Alright, so hopefully you recognize that integrand, and you know that the integral of 1 over x squared plus 1 is arctangent. So we get arctangent of x from 0 to b plus the limit as a approaches negative infinity of arctangent of x from a to 0. By the way, I split this up at 0. You can split it up at any number you want. There's no way to split infinity in half. It's just as big no matter where you go. I could split it at 1,000,000. I could split it at -5. Whatever's convenient, whatever seems easy. 0 is usually the simplest, but you don't have to do that. But if you do have a negative infinity and positive infinity, you do have to split it in two pieces. But it's up to you what that middle split point is. Or middle's not a good word, but you know what I mean. Alright, so let's plug in the top minus the bottom. Then we have to also do this side. The top minus the bottom. Arctangent of 0 is just 0, so we can simplify this to be the limit as b approaches infinity of arctangent of b plus the limit as a approaches negative infinity of negative arctangent a. So we're going to have to do these two separately because they're two different limits. Alright, so we'll do the first one. It's just arctangent x, and we're going to positive infinity. Okay, so I'm going to keep going. I think I recognize that what that number is becoming. Let's plug a big number in and see. Yes, that's clearly going towards pi over 2. So this side we're getting pi over 2 for our limit. Now let's do negative arctangent and go to negative infinity. So negative 10, negative 100, negative 1,000, and negative 1,000,000. We'll just jump up to that. I think that's right. Okay, so it is also going toward pi over 2. So we get pi over 2 for both pieces. Pi over 2 plus pi over 2 is pi. So this one again converges. Anytime we get a finite number, it converges. So believe it or not, you can take the limit under arctangent all the way from negative infinity to positive infinity, and all you get is pi. This is section 7.8 in our books. Questions that look like these are numbers 9 through 26.